In this video, we're going to solve this op-amp circuit. In this case, we're going to have a capacitor and it's going to make it a little bit more complicated to solve, but we can still do that. This is called the Integrator op-amp, and you'll see why that is by the time we've finished here. So we don't have any specific values for my resistor capacitor. We don't have specific value for the input voltage VI. So we're just going to try to find the output as a function of the input. So we have an ideal op-amp here. We know the rules say that the voltage at the positive terminal is equal to the voltage of the negative terminal. Since the positive terminal is hooked up to ground, that means it's 0 volts there. It's going to be 0 volts here. We're going to go ahead and do KCL at the negative terminal. So we have the current going left. That's the voltage we're at 0 minus the voltage you're going to, VI over R. Now the current going up, I can't do that same, voltage divided by resistance because it's a capacitor, not a resistor. It doesn't follow Ohm's law. However, we can still find the current to the capacitor. We know that for a capacitor, I is equal to C dV dt. So if this is our voltage here, then I would be C dV dt. But what is the voltage across this? Well, it starts at 0 volts and goes to V0, so that means my voltage there is 0 minus V0, or really it's just the negative of the output voltage. So when you take the derivative of that, the negative just comes through. So it's going to be negative C dV0 dt. So the current going up is a negative C, the derivative of the output voltage. And then the current going right, by the other ideal op-amp rule, the current going into the plus and minus nodes are both 0. So this becomes our starting equation. If I move things around, I would see dV0 dt. Move that to the right side. Divide by C, it's going to be a negative 1 over RC times the input voltage. And if I want to solve for the output voltage, I have to integrate here. So I'll integrate from some starting time to the current time. And we would then have, by fundamental thermal calculus, V of the final time minus V of the initial time is this integral over here. And since our final variable is t, we use some dummy variable, call it x over here. And the end of that result is going to be the output voltage, sorry, these are V0s here. The output voltage at a current time is equal to the output voltage at a starting time minus 1 over RC times the integral of the input voltage over that interval. And so what that means is this circuit here, when you're trying to find the output, it's going to be based off of the integral of the input voltage, whatever that may be. And that's why this is called the integrator op-amp. So you put whatever input function you want on there, and the output is going to be the integral of the input, scaled with this 1 over RC value is here, inverted with a negative sign, and then shifted based on whatever the starting voltage was. But regardless, we basically get the integral of the input on the output using the integrator op-amp.